In this video, I introduce a spectral normalization for GAN. Generative adversarial network has a stability challenge during its training. Spectral normalization is a method to stabilize the GAN training, which is determined by the Lipschitz continuity through normalizing weight matrices in the discriminator. GAN optimization is the minimum maximum problem where V is an objective function. Fixing the generator G, the optimal discriminator D star is calculated by using the data distribution and the model distribution. If we use a sigmoid as the output function for discriminator, and F is the feature vector of the last layer of a discriminator, the optimal F and the derivative of F star are computed by using data distribution and model distribution. The derivative of F star may be incomputable, so we can add some constraints on the derivative of F star. We search for a discriminator D from the key Lipschitz continuous function set, namely Lipschitz continuity is used to find the discriminator D satisfy the constraint Lipschitz normal for F, which means any x and x prime in the training data set satisfies the following inequality here. Suppose that a mapping G from H in to H out using definition of Lipschitz norm, we have this equation where sigma is a spectral norm of matrix A. So we can use this definition to calculate sigma. For a convolutional neural network, we have this G is equal to WH, and the Lipschitz norm of G is equal to sigma W, namely, we calculated the Lipschitz norm of W is equal to sigma W. If the activation function, the Lipschitz norm of AL is equal to 1, using the inequality here, we obtain the upper band sigma on the Lipschitz norm of F. Then now we can use this sigma to normalize the weight W. So we get the normalized weight W bar, which satisfy the sigma is equal to 1 and Lipschitz norm of F is bounded by 1. Sigma W is the largest singular value of W. Suppose that a U wave is randomly initialized for each weight W. The power iteration method is used to compute the right and left singular vectors. We calculate V from U and we calculate the U from V. We can then approximate the spectral norm of W using the pair of singular vectors, U wave and V wave. U wave computed at each step is used as the initial vector in the subsequent step. Here is the pseudocode for spectral normalization. For more details, please check with these references. Thank you. Bye.